We thought we understood 3IATLAS. It came from outside our solar system. It was a comet. It swept through our planetary neighborhood, passed around the Sun, and continued back into interstellar space. Case closed. Except it isn't. The longer scientists study the data collected during 3IATLAS's visit, the stranger the picture becomes. The water inside it has an unusual isotopic signature. The methane it released raises questions about where and how it formed. Its trajectory has produced a series of statistical coincidences that have attracted attention. And the chemical fingerprints embedded in its gas are pointing toward a birthplace that may have been extremely cold, ancient, and very different from our own solar system. 3IATLAS is getting stranger, and we need to look at the evidence. Let's start with the water. Water seems simple. Two hydrogen atoms bonded to one oxygen atom. But hydrogen comes in different forms. The most common form is ordinary hydrogen, with a single proton at its core. There is also a heavier form called deuterium, which contains a proton and a neutron. When deuterium replaces hydrogen in water, it creates heavy water or partially deuterated water. That matters because the ratio of deuterium to ordinary hydrogen can preserve information about the environment in which the water formed. In comets, that ratio can provide clues about the temperature and chemistry of the region where their original ice formed. This is where 3IATLAS becomes particularly interesting. A team using the Atacama Large Millimeter, Submillimeter Array studied the deuterium content of the water being released by 3IATLAS as it traveled through the inner solar system. The reported result was extraordinary. The deuterium to hydrogen ratio in its water was measured at more than 40 times the value found in Earth's oceans and more than 30 times the values typically measured in solar system comets. That is not simply a small difference. It suggests that the water incorporated into 3IATLAS formed under conditions very different from those that produced the familiar comets in our own solar system. The researchers concluded that its birthplace was likely an unusually cold environment with a very different chemical history. And that leads to an even bigger question. Where did this object actually come from? A separate study examined isotopes of carbon and nitrogen in 3IATLAS. Instead of looking at hydrogen and deuterium, researchers analyzed different forms of entirely different elements. The measured carbon isotopic ratio was approximately 147, while the nitrogen ratio was approximately 343. Those values are substantially different from the typical values measured in solar system comets. The researchers interpreted the combination as evidence consistent with formation in a cold, metal-poor environment. Metal-poor does not mean the object was made of metal. In astronomy, metallicity refers to the abundance of elements heavier than hydrogen and helium. Young galaxies and early generations of stars contained far fewer of these heavier elements. Over time, massive stars lived and died, exploding as supernovae and enriching their surroundings with carbon, oxygen, nitrogen, iron, silicon, and many other elements. Our Sun formed billions of years after that process had already been underway. But if 3IATLAS really formed in a much older, metal-poor environment, its chemistry could preserve information from a much earlier stage of galactic history. Its estimated age has been discussed in the range of roughly 10 to 12 billion years, although the exact age remains uncertain. That would make it dramatically older than Earth. Imagine that. Before our Sun existed, before Earth formed, before our solar system assembled, the material that eventually became part of 3IATLAS was already frozen somewhere around another star. Then, billions of years later, that material crossed interstellar space and entered our solar system. And then the James Webb Space Telescope looked at it. After 3IATLAS passed perihelion, Webb observed the comet with its mid-infrared instrument. The observations revealed water vapor, carbon dioxide, carbon monoxide, and methane. The methane was particularly interesting because it had never before been directly detected coming from an interstellar object. Methane is extremely volatile. It can escape from exposed surface layers relatively easily when conditions become warm enough. That means methane detected after perihelion can provide clues about deeper layers of the nucleus. As sunlight penetrated the comet's outer material, previously protected regions could begin releasing gases that had remained trapped for enormous periods of time. In other words, the sun effectively opened a window into the comet's interior. Webb measured methane production at substantial levels relative to water production during its observations. And the methane was only one part of the chemical puzzle. Earlier observations had already shown that 3IATLAS had an unusually high carbon dioxide to water ratio, with carbon dioxide accounting for a very large fraction of the observed gas production. Together, these observations paint a picture of an object with a chemistry very different from the comets we know best. Its water is unusual. Its carbon and nitrogen isotopes are unusual. Its volatile composition is unusual. And some of its deeper material appears to have a different chemical composition from its outer layers. That last point is important. A comet does not necessarily have the same composition throughout its entire interior. The outer surface can be altered by radiation, heating, and repeated exposure to the space environment. Deeper material can remain comparatively protected. When 3IATLAS passed close to the Sun, heat penetrated deeper into the nucleus and triggered the release of material that had remained sealed away. Telescopes observing it after perihelion therefore had an opportunity to study material that had been protected for an extremely long time. Then there is the trajectory. This is where the discussion becomes more controversial. Harvard astrophysicist Avi Loeb has highlighted a number of unusual properties of 3IATLAS and has argued that they deserve closer examination. The mainstream scientific interpretation remains that 3I-ATLAS is a natural interstellar comet. But some of the measurements Loeb has discussed are real observations, even though scientists disagree about what they mean. For example, the object's incoming trajectory has been described as being relatively close to the plane of the solar system. The probability arguments surrounding that alignment depend heavily on how the relevant population and selection effects are modeled, so claims of extremely tiny odds should be treated cautiously. The same applies to the object's non-gravitational acceleration. Comets can experience additional acceleration when sunlight causes ice to sublimate and escaping gas produces thrust. That process is completely natural. What attracted attention was the structure and persistence of some of the observed jets. High-resolution observations revealed multiple jet-like features extending from the coma. Their appearance and stability have prompted questions about the shape, rotation, and active regions of the nucleus. But unusual does not automatically mean artificial. Comets are complicated objects. Their surfaces are irregular. Their interiors are heterogeneous. Their rotation can change. Jets can originate from localized active regions, and viewing geometry can make natural activity appear surprisingly organized. Another frequently discussed feature involves Jupiter. Orbital calculations placed 3IATLAS on a trajectory that brought it relatively close to Jupiter's gravitational sphere of influence. Some analyses have emphasized how close the predicted encounter distance was to Jupiter's Hill sphere. But once again, an interesting numerical coincidence is not evidence of engineering. The correct question is whether the probability was calculated after accounting for how the object was discovered, how its trajectory was selected, and how many possible coincidences were examined. This is why most astronomers remain cautious. There is also an important negative result. Radio observations conducted by researchers associated with the SETI Institute and Breakthrough Listen searched for possible artificial signals. Candidate signals were investigated, but the surviving candidates were attributed to terrestrial or satellite interference. No confirmed artificial transmission from 3IATLAS was detected. That matters. If 3IATLAS is a natural comet, then its strange properties are telling us something fascinating about how diverse planetary systems can be. If someone proposes something more exotic, the burden of evidence is much higher.